Hey everyone, welcome to Maxima and Minima. Okay, this is Nicholas JMV, and we're going to talk about Maxima and Minima today and really get into this idea of what we call optimization. Okay, so our first slide here, our page, is really just kind of a lot of definition here. Okay, what is a maximum or minimum value of a function? Well, it occurs at a point where the derivative of a function is zero or where the derivative fails to exist. So for example, if I have this nice function, what we're looking for is a relative max, they call them, or minimum. If I draw this, I'm talking about where the horizontal, the derivative is zero. So like right here and right here, they happen on hills of functions. Okay, so this could be like a minimum value, not necessarily, it's not absolute, and this would be your local max value. And we'll get into talking about this later on with curve sketching and things like that. But that's the idea of what they're talking about here. Okay, so there are two different kinds of maxima and minima. There are relative and absolute, and these would kind of be your relative examples right there. Okay, so a relative or local max or min means the curve has a horizontal line at that tangent, but is not the highest or lowest value that it attains. So when I look at this, it's got a slope or a derivative of zero, but it's not the max point. Look, this would go off forever. Even points up here are higher. Even points down here are lower. So that's what they're talking about, that purple definition there. Okay. And finally, with the absolute. Okay, when you look about absolute max or min, that's the other thing. Is either an artificial point or an endpoint. A relative max can also be called an absolute max. So an absolute max or min occurs at either an artificial point somewhere on the graph or at an endpoint. So like here would be absolute max would be up here, absolute min down in this area. So absolute max, the way I drew this, would be up here. Okay, could be on an endpoint, but it would be an absolute max up there. Okay, this is important too. If a function has a critical value at x equals c, then that value is a relative maximum if the second derivative's value at c is less than 0, and it's a relative minimum if the second derivative at c is greater than 0. This is going to help us with these optimization problems to determine if the critical value we find is a minimum or a maximum. So let's look at this idea of optimization. Okay, this is so they're maxima and minimum problems. Okay, so I'm looking and I have a manufacturing company has determined that the total cost of producing an item can be determined by the equation C equals 8x squared minus 176x plus 1800. X is the number of units that the company makes. How many units should the company manufacture in order to minimize the value? So let's look at how we would do this problem. So what we're going to do is look at the derivative, okay, because that can tell us our critical value. So we have C equals, and now this is just a polynomial function, so the derivative is going to be pretty easy. So I go ahead and take my derivative, and C prime is going to be equal to 16 x minus 176. Okay, and if I look at the 0 there, if I want to find the critical value by setting C prime equal to 0, I can do that. And if I solve this linear equation, I'm going to get a value. If I add 176 to both sides, looks like I get x is equal to 11. Okay, so that's my critical value. So we have to determine now if this value, if this is the number of units we're going to manufacture, is going to be actually a minimum. Okay, and to do that, we need to look at the second derivative. Okay, so if I take C prime, and I know that's 16x minus 176, if I take the second derivative, I get 16. Now that means C double prime is greater than 0. Okay, so that means x equals 11 is going to be a minimum value. Okay, so what that tells us is that the answer to this is going to be 11 units. The manufacturer needs to produce 11 units to minimize that cost. So using the first and second derivative here. Okay, so there's our first problem. Okay, and here's now our second one. A rocket is fired into the air and its height in meters at a given time, any given time t, can be calculated by using the formula here, 1600 plus 196t minus 4.9 t squared. Find the maximum height of the rocket and the time at which it occurs. Okay, so we're going to look at the first derivative. So h prime of t, the derivative of a constant is 0. The derivative of 196t is 196 minus 9.8t. Now we have to find the critical value by setting the derivative equal to 0. Okay, so I go ahead and do that. And if I go ahead and solve this out, I get t is equal to 20. So that's not quite our answer. Okay, we know that the critical value is 20. We're hoping that it's a maximum, so we're hoping that the second derivative of h is negative. So h double prime of t, the derivative of a constant is 0. The derivative of 9.8t is 9.8, but it's negative minus, and there we go. So what this tells us is that at this critical value, h double prime is negative. Okay, well, it's always negative, so this is always going to be a max. So this is a max. So we've got our t. After t was in, I think, seconds. The height was in meters, and t can be calculated at a given time. It doesn't say the time, so we'll just say t is 20, maybe probably seconds. But we want to know the maximum height. So we know that t is 20, and to get the maximum height, we have to find h of 20. We've got to plug that back into the original. So you get 1600 plus 196 times 20 minus 4.9 times 20, and that's squared. I'll let you calculate that out, but I get approximately 3,560 meters is the maximum height there when, at 20 seconds. Okay, so that's our second example. Our last example, nice little drawing. Max wants to make a box, okay, with no lid from a rectangular sheet of cardboard that is 18 by 24, okay, and we're cutting out x's, cutting out a square on the side from each corner of the sheet and folding up the sides. Find the value of x that maximizes the volume. So we need the derivative and we want maximizing, so we want to think about hopefully where the second derivative is negative. So let's go ahead and start this example. It takes a little bit of time. So here's our picture. We know that the width here is going to be, the whole thing is 18, but you got to go minus x minus x. So the width is 18 minus 2x. Okay. The length is 24 minus 2x for the same reason. You cut out those two x's there. And then the depth, they tell us, when they fold there, is going to be just x. So when you look at this, we want to maximize the volume. The volume of this rectangular shape, prism, I guess, I don't know if prism is the right word, is x times 18. You got to multiply length times width times height. And we're going to go ahead and do that. So there is my volume. Okay, if I simplify this out, multiply it out, I get 4x cubed minus 84x squared plus 432x. Okay, so I've got my volume, but now I got to take dv dt. I need the critical values, and at those critical values, I can determine if there's a max or min. Dv dx, I'm sorry. So I take my derivative, I get 12x squared minus 168x plus 432. Nice little polynomial power rule. Okay, again, I want the critical value. Set your derivative equal to 0. Now this is where it gets a little tricky because if I factor out a 12, I get x, excuse me, x squared minus 14x plus 36. And when you think factoring, can't factor. So I set up the quadratic formula and I get 14 plus or minus the square root of 196 minus 144 over 2. I'm depending you guys to know how to do that. Okay, this is your A equals 1, B equals 14, C equals 36, and you know that formula by now. So I get approximately, when I simplify the math out, I get 3.10, or excuse me, 3.4 and 10.6. Now 10.6 does not work, okay? And it would have a tough time here. Okay, 18 minus 2 times 10.6. Okay, oops, it'd have a difficult time up there. Okay, so our only value we can use is 3.4. Okay, so at 3.4, okay, let's look. So dv, d squared, dx squared, okay, is going to be, so at 3.4, we're going to have, let's look, we're going to have 24x minus 168. And then if you plug 3.4 into this, minus 168, you get a negative 86.4. So that means that this is a maximum value. Okay, so once we have that as our maximum value, this is just a confirmation. We can finish up this problem. Okay, we know that the volume is equal to x by 18 minus 2x because they want the dimensions times 24 minus 2x, and we know that x is 3.4. When you plug 3.4 into each of these x's, you get the dimensions of we can do it. So we can do 11.2 by 17.2 by 3.4, length, width, and the height, the depth there. Okay, so there is the dimensions. 3.4 maximizes the volume of that box. So anyway, that is maxima and minima and its relationship to optimization. If you have any questions or comments, please let me know. We'll see you next time.